Okay, so today we're going to talk about section 1.1. We'll do 1.2 another day. So section 1.2 is parent functions and transformations. A parent function is just the most basic function in any function family. There is one type of parent, or one parent function for each different type of function. And these aren't the only types, but they're the four that we're going to look at today. And then functions that belong to the same family share key characteristics. So that's why we study them in order to graph more complex functions using transformations. So if we look at the four functions we have listed here, a constant function, the parent function of that is just the rule f of x equals 1 or y equals 1. It's just a horizontal line through y equals 1. And then for linear, we have f of x equals x. That's just a diagonal line through the origin with a slope of 1. And then the two that we're really going to focus on over the next two chapters are absolute value and quadratics. So for absolute value, the parent function is f of x equals x. This graph has a vertex at the origin. That's the name of where it changes direction, is the vertex. On the right side, there's a slope of 1, so it goes up 1, right 1. And then on the left side, it's just flipped over, so that slope becomes negative 1. The domain for any absolute value function at all is always all real numbers. And you can shorten or use this symbol as all real numbers instead of writing it out every single time. It's just an R with a line through it. And then for range is based on all the possible y values of the function. So because this graph has a low point, there will never be any y values down here underneath the x-axis. So that's why our range has to be greater than or equal to 0. It can be equal to 0 like it is right here, or it could be anything greater than 0 because these lines will go up and up and up forever and ever. So you'll get up to basically infinity. For quadratics, so f of x equals x squared is our parent function. And it looks similar to absolute value, it's just a U shape instead. It's still all real numbers for domain, because domain is just what possible input values or x values can I have. And just like absolute value, I can put any value for x in and get a real solution out. And then if we look at the graph, both of these graphs are extending in the x direction, so left and right, forever and ever. Even though this graph gets really steep, it'll never go fully vertical, so the x values will continue to increase and decrease as we go away from the vertex. And then range is still y is greater than or equal to 0 because we have this low point. This graph isn't going to randomly have points down here, so there will never be negative y's. So y's can either be equal to 0 or anything greater than it or above it. So we're just going to graph the parent function really quick. I know it's right here for you, but I kind of want to just talk about how we get these points in case we don't really remember it. So we'll use a table, x and f of x. For my x values, I'm going to use -2, -1, 0, 1, and 2. So each time I substitute in one of these x values into my parent function, I just have to take the absolute value of that x. So the absolute value, or if I substitute it in x equals -2, I'm just taking the absolute value of -2, which is +2. If I substitute in x equals -1, take the absolute value of that, which is +1. Absolute value of 0 is 0. Absolute value of 1, 1. Absolute value of 2 is 2. And then that gives me 5 points that I can plot to create a pretty good looking graph. So -2, 2. From the origin, I'll go left 2, up 2. For -1, 1, from the origin, I'll go left 1, up 1. 0, 0 at the origin. 1, 1, I'll go right 1, up 1. And then 2, 2, I'll go right 2, up 2. And you'll notice that the graph looks pretty symmetric. It should be symmetric if it's an absolute value graph. Okay, so moving down to example 1, we're going to graph these first few functions just with a table, and then we're going to kind of talk about what is causing these different changes from the parent function. So for 1, it's g of x equals absolute value of x plus 2. So whatever my x is, I have to take the absolute value of that and then add 2 after. So when x equals -2, the absolute value of -2 is +2 plus 2 is 4. And you can always just write out the math off to the side if you would like to. So like if I wanted to do that, I would substitute in x equals -2 into my absolute value bars, and then I would add 2. So the absolute value of 2 is +2 plus 2, and that's how I get this 4. So you don't have to do it in your head, but you can if you want to. So when x equals -1, the absolute value of that is +1 plus 2 is 3. When x equals 0, absolute value of 0 is 0 plus 2 is 2. When x equals 1, absolute value of 1 is 1 plus 2 is 3. When x equals 2, absolute value of 2 is 2 plus 2 is 4. So now I have 5 points that I can graph. You really do want to get at least 5 points for an absolute value graph. It just makes it look a lot cleaner. So -2, 4. From the origin, I'll go left 2, up 4. -1, 3. From the origin, I'll go left 1, up 3. 0, 2. I'm not going to go left or right at all. I'm just going to go up 2. 1, 3. I'm going to go right 1, up 3. And then 2, 4. I'll go right 2, up 4. And then go ahead and connect those points. My graph, it looks a little weird because I don't have graph paper, but it should be symmetric. So if we talk about domain, remember, domain for any absolute value graph is all real numbers. And the reason is because I can pick any number for x. I can pick like -1 billion and plug it in here, and I would still get a real answer. It would be like a really big answer, but it would still be a real number. So domain is all real numbers. And again, domain is what your possible x values are. And then range is what your possible y values are. So if we look at the graph, we can see that there's never going to be any points down here. So the range is going to be cut off in some way. So the lowest point is at y equals 2, and then it goes up from there. So our range would have to be y is greater than or equal to 2. So one thing about range is, especially with absolute value and quadratics, it's always going to be related to the y coordinate of the vertex. So like my vertex is 0, 2, so my range is related to that 2. And then for example 2, h of x equals the absolute value of x plus 2. We're not going to use the same -2 up to +2, and I'll explain why after we graph it. We're going to use -4 up to 0. So h of x equals absolute value of x plus 2. Again, we're just substituting this x in and then evaluating the function there. With example 1, we took the absolute value of x first and then added 2. With this one, we're going to take x, add 2 first, and then take the absolute value. So when x equals -4, -4 plus 2 is -2, and then the absolute value of that is +2. When x equals -3, -3 plus 2 is -1, the absolute value of that is +1. When x equals -2, -2 plus 2 is 0, so the absolute value of that is 0. When x equals -1, -1 plus 2 is 1, the absolute value of that is 1. And when x equals 0, 0 plus 2 is 2, absolute value of that is still 2. So now we have 5 points that we can graph. So x equals -4, h of x equals 2, so from the origin we'll go left 4 up 2. -3, 1 will go left 3 up 1. -2, 0 will go left 2, but we will not go up or down at all. -1, 1, I'll go left 1 up 1, and then 0, 2, I'm just going up 2, and then connecting those points. So the reason that we can't just always use -2 up to +2 is because say I had just used those numbers, so -2 up to +2, I would have never gotten this side of the graph. My furthest left point would have been -2. And then the other points that would have gone would have continued along this line, so it would have looked like I just had a straight line, not a V. So we'll kind of talk about how you know what values that you put in a table, and at some point, or hopefully soon, we won't even really need to graph using a table. So domain is still all real numbers. I can have any possible x value in there. And then range The lowest point on my graph is at y equals 0 right here, and the graph goes up from there, so y is greater than or equal to 0. If for whatever reason this graph went downwards, if it was flipped over the x-axis, your range would become y is less than or equal to 0, because that 0 would be a high point. Okay, so this next section is, if we were in class regularly, this would be something that you would investigate on your own. So if at all possible, I would prefer that you guys pause the video and complete these problems now. And then we'll go through and check them together. So I'm gonna go through these pretty quickly because you should have them done by the time you watch this next part. And then we'll kind of talk about what the different transformations look like. Okay, so number 1, f of x equals absolute value of x minus 4. When I plug in -2, absolute value of that is positive 2. 2 minus 4 is -2. When I plug in x equals -1, absolute value of -1 is 1, minus 4 is -3. When I substitute in 0, absolute value of 0 is 0, minus 4 is -4. Absolute value of 1 is 1, minus 4 is -3. Absolute value of 2 is 2, minus 4 is -2. So now I have 5 points that I can plot. So -2, -2, -1, -3, 0, -4, 1, -3, 2, -2. Then now I can look at domain and range. So domain is going to be all real numbers. Same thing, it's always all real numbers for absolute value. Range is my lowest possible y value is -4. So my range has to be y is greater than or equal to -4 because that's our lowest possible point. It could be anything above that. So if we compare this back to the parent function that we just did on the first page, the parent function starts at 0, 0, and then it just has a slope of 1 on both sides. This graph has the same, I guess, like width, so it has the same slope on either side. It's just pushed down 4. And the reason it's pushed just down 4, just slid downward, is because this -4 outside of the absolute value bars. So how does this graph compare to the parent function? We just kind of talked about that. It's just translated down. It's shifted down 4, or our math or textbook term is translated. Translated down 4 units. For number 2, f of x equals absolute value of x minus 3. So here's our x values. So absolute value of 1 minus 3. 1 minus 3 is -2. The absolute value of that is positive 2. When I substitute in 2, 2 minus 3 is -1. Absolute value of that is positive 1. When I substitute in 3, 3 minus 3 is 0. Absolute value of that is 0. 4 minus 3 is 1. Absolute value of that is still 1. And then 5 minus 3 is 2. And the absolute value of that is still 2. So I have the point 1, 2. So I'm going right 1, up 2, 2, 1, right 2, up 1, 3, 0, 4, 1, and 5, 2. So now I can see my graph, my domain still looks like all real numbers. It's still going to extend in either direction to positive. X is positive infinity, x is negative infinity. That just means that x will always be increasing and decreasing. And then range, my lowest point here is at y equals 0. So my range is going to be y is greater than or equal to 0. And then if we compare this graph to the parent function, remember the parent function starts at 0, 0. It has the same slope on either side, but it starts on 0, 0. So this graph has been shifted or translated 3 to the right. And the reason that this graph has been shifted left or right is because this -3 is inside of the absolute value bars. So when we're moving up and down, the number that we're adding or subtracting is outside of the absolute value bars. When we're shifting left or right, that number is inside of the absolute value bars. So one other thing to notice is our graph technically shifted to the positive direction. Right is the positive direction when we're talking left or right. However, in the absolute value bars, we have x minus 3. And that actually has nothing to do with like absolute value making things positive. What it does is we have to basically flip the sign of anything that's in there. So say this was an x plus 3, the graph would have been shifted left 3. And we'll talk about that more later on. So number 3, f of x equals 2 times the absolute value of x. Absolute value of negative 2 is positive 2, times 2 is 4. Absolute value of negative 1 is 1, times 2 is 2. Absolute value of 0 is 0, times 2 is still 0. Absolute value of 1 is 1, times 2 is 2. Absolute value of 2 is 2, times 2 is 4. So we're taking the absolute value first and then multiplying it by the 2. So now I can graph these 5 points. So negative 2, 4, negative 1, 2, 0, 0, 1, 2, and 2, 4. Domain, again, still all real numbers. That will not change for absolute value. For range, my lowest point is at y equals 0, and the graph goes up from there. So my range is y is greater than or equal to 0. How does this graph compare to the parent function? Remember with the parent function, our slope on either side was 1 and negative 1. If we look at our new graph, on the right side, this slope is 2. It's no longer going up 1, right 1, up 1, right 1. It's going up 2, right 1. And then on the other side, it's just negative 2. So the graph has been what we call stretched. So it's more narrow than our parent function. But that's not really the words that we use for transformations. What we talk about is in terms of stretch versus shrink, or stretch versus compressed. And sometimes it seems like stretch should be the wider one, but the reason it's stretched for when something is more narrow is because it's basically this parent function has been stretched up away from the x-axis. It's been pulled up away from the x-axis, so it's been stretched. If we look at number 4, f of x equals absolute value of, 1/2 times the absolute value of x. So we're going to take the absolute value of all of our x values and then multiply that by 1/2 or divide by 2. So absolute value of negative 2 is positive 2 times 1/2 is 1. Absolute value of negative 1 is 1 times 1/2 is 1/2. Absolute value of 0 is 0 times 1/2 is 0. Absolute value of 1 is 1 times 1/2 is 1/2. Absolute value of 2 is 2 times 1/2 is 1. So now we have 5 points. Just go ahead and estimate where the 1/2s go to the best of your ability. But negative 2, 1, left 2, up 1. Negative 1, 1/2, left 1, up half. 0, 0, 1, 1/2, and then 2, 1. So now this graph, when we compare it to the parent function, which again goes up 1, right 1, up 1, right 1, it looks, I skipped domain and range, we'll go back to that. It looks like it's squished, or it looks like really wide. So we'll say it's more wide, but the math term that we use in order to describe this type of transformation is either a shrink or compressed, either way. So we'll say it's shrunk / compressed. Whatever you're more comfortable with, I am fine with. And again, it's because that parent function is being like smushed towards the x-axis. In both stretch and compress, we're talking about in terms of the x-axis. So domain, still all real numbers, and then range, my lowest point is still y equals 0. It has not been shifted up or down at all. So my range is y is greater than or equal to 0. last one of these is number 5, so f of x equals the negative absolute value of x. That means that we have to take the absolute value of each of our x values and then make it negative after. So the absolute value of negative 2 is positive 2, but when I make positive 2 negative, or when I flip that sign, it becomes negative 2. Absolute value of negative 1 is 1. When I make it negative, it becomes negative 1. Absolute value of 0 is 0. Can't have a negative 0. Absolute value of 1 is 1. Make it negative. Absolute value of 2 is 2. We got to make it negative. So it is negative 2. So now I can plot those points. So negative 2, negative 2. Negative 1, negative 1. 0, 0. 1, negative 1. And 2, negative 2. So domain, again, the domain is not going to change. As long as we're talking about absolute value, it's not going to change. So it's still all real numbers, and that just means that I can pick any x value, substitute in, and get a real number out. And then range, my vertex is still at y equals 0, but the graph goes down now. So I can't say that y is greater than or equal to 0 because there's actually no y values greater than 0 that are up here. So my range will be y is less than or equal to 0. There can be, all of these are possible y values, so like y could be negative 1 or negative 2, but it'll never be greater than 0. And then how does this graph compare to the parent function? It has been flipped or reflected over the x-axis. So we're just going to do a quick little recap of those problems. You go back to the first set. So number 1 was translated down 4 units. And what translated the graph down 4 units was the fact that there was a -4 outside of the absolute value. Number 2 was translated right 3 units. And what translated it right was the fact that there was a -3 inside the absolute value bars. Had this been an x plus 3 in absolute value, it would be shifted left. For number 3, this graph got stretched, and I'm going to add that it was stretched by a factor of 2. And what stretched it by a factor of 2 was this 2 out in front of the absolute value bars, was that 2 being multiplied by the absolute value. For number 4, I'm going to add that it was shrunk or compressed by a factor of 1/2. And again, what did that was the fact that there was a 1/2 multiplied in front of the absolute value bars. So with stretched and compressed, or stretched and shrunk, both times it's the same operation that does that. What changes it between stretched and shrunk or stretched and compressed is the actual number that you're multiplying by the absolute value. So like for number 3, when we multiplied it by 2, anything greater than 1 is going to be a stretch. So this coefficient is something we actually usually call A, and we're going to get more into that later. So when A is greater than 1, you have a stretch. And when A is less than 1 but greater than 0, so when A is between 0 and 1, it's a shrunk or compressed. Or I'm going to say shrink or compress. And we'll talk about that more, and I'll keep kind of reminding you guys of that later on. And then lastly, for number 5, we had a reflection. And what caused that reflection was the negative out in front. So that's why when we talk about stretch and compress, it's not just A is greater than 1, A is less than 1. It's just we talk about in terms of whatever the positive or whatever the absolute value of the number in front is. So if this number is greater than 1, it's stretch. If it's between 0 and 1, If it's between 0 and 1, like a fraction or a decimal, it's shrunk or compressed. And then if there's a negative number out in front, that reflects it. That just flips it over the x-axis. So last couple problems for this lesson is we're going to talk about kind of how you would, I guess, write equations with transformations without even worrying about the graph. So number 6, make a prediction of on what the graph of f of x equals x minus 4 plus 5 will look like in comparison to the parent function. What will the domain and range be? So if we look at f of x equals absolute value of x minus 4 plus 5, I have two different transformations going on here when I compare it to the parent function f of x equals the absolute value of x. I have two extra pieces. I have this minus 4, and then I have this plus 5. So we have to go back and think about what happens when we have something inside of the absolute value bars being added or subtracted. So both of these transformations were on the first set of these problems. So when I had something inside of the absolute value bars, it translated my graph left or right. When it had an x minus 3, it translated 3 to the right. So because I have an x minus 4, the parent function will be translated 4 to the right. And then when I'm trying to figure out what this plus 5 does, the very first problem that we did had a number being added or subtracted after the absolute value bars. This minus 4 moved the graph down 4. So subtracting something outside of the absolute value bars moves it down. That means that adding something outside the absolute value bars will move it up. So it's translated 4 right and 5 up. And then we can talk about domain and range. So domain is still, again, it's always going to be all real numbers for any kind of absolute value graph. And then range will look a little different. So because we moved this graph up, the range will not be like y is greater than or equal to 0 because this graph moved up 5. So if you can't picture the parent function in your head, which that's something you're going to want to try to be able to do as we work on this more. Here's our parent function. We shifted it right 4 and up 5. So the new vertex would be up here at 4, 5. That means that the new range got moved up 5 also. So the range is y is greater than or equal to 5. And then for number 7, so we just have to write a few equations, and this is the last problem for this set of notes. So let f of x equal the absolute value of x, where x can be any real number. Write a formula for the function whose graph is the transformation of the graph of f given by the instructions below. So we're going to call our transformation function g of x. So I'm going to start with g of x. And I want to take my parent function f of x equals absolute value of x, and I want to move it up 5. So remember, what moved things up and down was adding something after the absolute value bars. So I would have the absolute value of x plus 5. So this plus 5 after the absolute value bars moves it up. And then for B, a vertical scaling or a vertical stretch with a scale factor of 5. So remember our stretch by a scale factor, by a factor, that was when we had a coefficient or a number multiplied in front of the absolute value bar. So this will be the same thing. So g of x in this case would have to be not just the absolute value of x, but 5 times that, 5 times the absolute value of x. For C, a translation left 5 units. So again, start with g of x. And then when I am shifting things left or right, I have to put something inside of the absolute value bars with the x. So when we shifted, sorry, I keep going back to these just to kind of show you an example. When we shifted right 3, it was x minus 3. But for this problem, we're shifting left 5. So it cannot be x minus 5, it has to be x plus 5. So x minus a number inside the absolute value bar shifts it right, x plus a number inside the absolute value bar shifts it left. A vertical scaling or a vertical shrink with a scale factor of 1/5. That's going to look just like the vertical stretch, remember? So there's just that coefficient out in front. Instead of 5, this time it's 1/5 though. So g of x equals 1/5 times the absolute value of x. And then a vertical scaling with a factor of 1/2, and then a translation 3 units to the right. So we have 2 different steps here and 2 different transformations that we have to include. So the vertical scaling with the scale factor 1/2, remember, vertical scaling, vertical shrink, whatever you want to call it, that's just where you have a coefficient out in front of the absolute value bars, or a number multiplied out in front. So that's 1/2 times the absolute value of x, but we have a translation 3 units right also, so we have to include that 3 somewhere inside the absolute value bars. Since we're going right, it'll be x minus 3.